Physics Part 412, the production of X-rays. Well. Whenever a charged particle is accelerated, electromagnetic radiation is emitted. This radiation is known as Bremsstrahlung radiation or breaking slowing down radiation. The larger the acceleration or deceleration, the greater is the frequency of emitted photon. X-ray photons may be produced by bombardment of metal targets with high-speed electrons. Electrons are first accelerated through a potential difference of several thousands of volts, that they have high energy and high speed. This acceleration is, however, not sufficient for X-ray radiation to be emitted. The high-speed electrons strike a metal target, which causes the electron to change direction and to lose kinetic energy very rapidly. Large deaccelerations are involved that give rise to the emission of X-ray photons. It should be remembered that not all of the energy of the electrons is emitted as X-ray photons. The majority is transferred to thermal energy in the target metal. A simplified design of an X-ray tube is shown in the figure. A metal filament is heated using a low voltage supply and electrons are emitted from the filament. This is called the thermionic effect. The electrons are then accelerated towards the target, constructed of metal with a high melting point. The electrons are accelerated through a large potential difference of the order of 20 to 90 keV. When the electrons are stopped in the metal target, X-ray photons, the Bremsstrahlung radiation, are emitted. The X-ray beam passes out of the tube through a window that is transparent to X-rays. The tube is evacuated and is made of a material that is opaque to X-rays. The tube is evacuated and is made of a material that is opaque to X-rays. This reduces background radiation around the tube. The anode is earthed. The anode is earthed and the cathode is maintained at a high negative potential so that the equipment is at earth potential. Since the majority of the energy of the electrons is transferred to thermal energy in the anode is either cooled or is made to spin rapidly so that the thermal energy is dispersed over a large area of the target. Control of the X-ray beam. In order that the optimum X-ray image may be obtained, both the intensity and the hotness of the X-ray beam need to be controlled. Number one, the intensity is the wave power per unit area, and this affects the degree of blackening of the image. Number two, the hotness is the penetration of the X-ray beam, which determines the fraction of the intensity of the incident beam that can penetrate the part of the body being X-rayed. In general, the shorter wavelength of the X-ray, the greater their penetration. A typical X-ray spectrum showing the variation with wavelength of intensity of an X-ray beam is shown in the figure. The spectrum has two distinct components. First, there is a continuous distribution of the wavelengths with a sharp cut off at the shortest wavelength. Second, sharp peaks may be observed. These sharp peaks correspond to the emission lines spectrum of the target metal and are therefore characteristics of the target.